what we're going to do today is we're going to have the lesson you've been looking forward to all semester, the last one. And we're going to talk about hypothesis tests for correlation and regression. And at the end of class, then I'm going to give out your take-home test. I've got them all right here already. Your take-home test will be due on Monday. After you complete your take-home test, oh shoot, I don't have a pen. After you complete your take-home test, then you're going to make a copy of it, or else write it all over onto a sheet of paper, whichever is your choice. And you're going to turn in the test I'm giving you. You're going to sign it, turn it back into me, but then you're going to have a copy of your test. And what I'm going to do is I'm going to group you up with other people and give each group, probably a group of maybe 3 or maybe 4, one copy of the solutions to that test. And then you're going to go over your test to see what you missed, and I'll go around to everybody and help you make corrections and figure out what you might have done wrong. Okay? And then next Wednesday, we'll review for the final exam, and I will have posted by then the practice final exam and the answers, so we can go over any questions you've got on reviewing for the final. I'll also have on Monday a sign-up for times if you want to take a makeup test or retake a test. I'll have a list of times that you can sign up to do that. Okay?
So do we have, when we get the test today, do we take pictures of it and submit it and show me?
No, you're going to turn that paper test back in. Now, if you want to take pictures of it for that to be your copy and put them in Shovie or whatever you want to do with that, that's fine. But keep a copy for yourself.
And then you'll grade it?
I will grade it, but I won't have the grades done. Maybe I hope to have them done by Wednesday, our last day. But if not, then at least you'll have an idea of how you did, and I can just tell you what your score was. Okay? So what we're going to do in this chapter is we're going to introduce methods for determining whether a correlation exists between pairs of data. A correlation is basically an association, and for linear correlations, the other step that we're going to take is we're going to identify an equation that fits the data and use that equation to predict the value of one of the variables in it if we have a value for the other variable. And then we're not really going to do that last thing about predicting intervals and analysis of the actual values. We're not going to do the error analysis. So in your notes, the first part that we're going to go through is going to be just getting some definitions. So a correlation exists between two variables when the values of one are somehow associated with the values of the other one in some way. For example, some of the data that we collected back at the beginning of school, we collected your height, measured with a tape measure in inches, and then we measured your arm span from fingertip to fingertip in inches. There is a relationship between that data. And the relationship isn't only because it's paired data, because each pair of data came from one person, but a person that is taller generally has a wider arm span, and a person that's shorter has a shorter arm span. Similarly, tall people tend to have longer feet. Now, that's not always true. It sometimes can be true. But your size of your foot and the size of your shoe, generally there is a linear correlation between the number we use to quantify your shoe size and how long your foot is. Because longer feet are going to need bigger shoes, which is a bigger shoe size. So there is a relationship between lots and lots of different kinds of data. That relationship is a linear relationship if you plot the paired data points that you have, and those points seem to follow a linear pattern. And we talked about that back in chapter 2. So we're going to look at scatter plots. And by looking at scatter plots, we can usually see the relationship between the two variables, if there is one. So we're going to talk a little bit in these next few slides about what the relationship between the data is. So in this first one, we've got a picture of a scatter plot that we think that the data has a positive correlation. And what that means is that the general pattern of those points isn't necessarily that they'll all fall on one single straight line, because they won't. It's pretty obvious that they don't fit a line. Not every single one would fall on the line. But they do tend to go uphill if you read from left to right. So going from the lower left corner to the top right corner with the data kind of clustered together indicates that there's a positive correlation. And in this case, this particular scatter plot has a correlation coefficient R that we're going to talk about in more detail in a few minutes. That is a positive number, and it's positive 0.851, which means it's close to 1, and we're going to learn that R values that are close to 1 are an indicator of having a strong positive relationship. The scatter plot in B has a negative correlation because it travels from the upper left corner down to the lower right corner. So its correlation coefficient is also negative, and it's very close to -1. It's negative 0.965. Now the other link here is that if we did fit a line to plot A, that line would have a positive slope. So positive correlation, if we come up with an equation of a line that fits that, that line will have a positive slope. And the negative correlation means that if we fit a line to that data, if we find an equation for that line, it's going to have a negative slope. The little picture over on the side basically says there's no correlation because there's no pattern. It just looks like paint splatters. There's no real pattern among the data, and the only line I'm likely to be able to fit through that data would just be a straight horizontal line right through the middle of it. And I wouldn't hit very much of it if I did, which is an indicator that there's no relationship between the two sets of data. And R equals 0 indicates that there is no relationship. It also indicates that the slope of the line that would be fit through there would have to be a 0 slope. It would have to be just a flat line, because it wouldn't fit any better than any other line. The scatter plot D you don't have in your notes. I just put this one in here to explain to you that we're looking for linear relationships. And plot D does exhibit some kind of a pattern, but that pattern isn't linear. It's a different kind of a pattern, and we couldn't fit a straight line to that. We would have to fit some kind of a curve to it. So these are the requirements for linear correlation. The sample of XY data has to be a simple, random sample of quantitative data. It has to be a simple, random sample, and you may not find this exactly where you are in your notes. It may not be in your notes. The sample has to be from a simple, random sample. Well, that's been true for the whole entire course. We always want simple, random samples. And since these are going to be paired in some graphable way, then we need to have that data be quantitative. It needs to actually be real numbers that measure something. We have to be able to look at a scatter plot to confirm that there does appear to be a straight line pattern before we do anything else. And if we notice that there are outliers, in the problem that we did last class, you notice we had an outlier. If we find outliers, we should remove them if we know for sure that it's an error. But even if we don't know for sure it's an error, we should also calculate the value of R with and without the outlier to see how much influence that outlier has on the rest of the relationship. And one caution throughout all of this, remember that the methods in this section are only going to apply to linear correlation, not any other kind. There are other kinds, but we only study linear correlation in this class. So if you conclude by looking at the scatter plot there doesn't appear to be a linear correlation, then there might be some other pattern available, but we can't go any further with the problem. The problem that you'll have on your take-home test will be a set of data that has some kind of relationship, and if it has a relationship, it will be a linear relationship. So these are the properties of the correlation coefficient. The first one is that the values of R are between -1 and 1 inclusive. R measures the strength of that relationship, and the way that it measures it is that the values of R close to -1 or +1 indicate a strong linear correlation. Values of R that are close to 0 represent a weak or no linear correlation. And also be aware, as I said before, R is very, very sensitive to outliers. They can dramatically affect its value. They can affect its value a lot. When we're interpreting R, we're going to take the value of R and square it, and that's going to give us the proportion of the variation in Y that's explained by the linear relationship between X and Y. And this is 3 common errors that may involve correlation. The first error is that it's wrong to conclude that correlation implies causality, because it doesn't. Being taller doesn't cause you to have long feet, or worse yet, having long feet doesn't cause you to be tall. It just happens to be there's a connection between the two. Okay? Getting older doesn't cause you to make more money, even though people who have had more birthdays do tend to make more annual salary. But the reason isn't just because they had more birthdays. It's because with the passage of time, they gain experience in their job, or maybe they take better jobs. So it's related to time passing, but it's not just because of the birthdays. You need to understand that averages suppress individual variability, and that may make a higher correlation coefficient, even though there's going to be some values that don't fit. And there may be some relationship between X and Y, even when there's no linear correlation. It may be a different kind of relationship. But the big one is this one. Remember that correlation does not imply cause. It doesn't necessarily say there's a cause and effect relationship. Now we're going to do a formal hypothesis test. And at this point, I'm going to stop with the PowerPoint, and we're going to work some examples. And I think that's about the best I'm going to get. Since I managed not to bring any pens with me, and I'm not seeing one up here, I'm going to go see if I can salvage one or scarf one from the next classroom. I'll be right back. Let me pause the recording while I do that. So we'll go ahead and finish up the rest of our examples. We've got 3. Example 2 is about a train station in Connecticut, and Connecticut has 2,804 commuters. That would be people that are driving in from outside the city to catch a train to go to their job every day. And the data list shows the number of commuters and the number of parking spaces at other stations. Not at the Metro North station, but at other stations. So when there's a lot of commuters at the Metro North station, their parking lot is full, but the other parking lots aren't. The other parking lots would not be being filled up with those. So what happens in this case is that when there's a lot of commuters at this station, there's going to be a lot of parking spaces left open at the other stations. And when there's not very many commuters at this station, because they went to the other station, then the number of parking spaces at the other stations is going to drop down. So we're going to make a scatter plot of the relationship between these two sets of data. So we're going to enter the data into the calculator. Just go Stat and Edit. And this is a little longer list than what I already have in there, so I'm just going to type over it. And one thing I'm going to caution you about, be very careful that you double check your data after you've entered it, because if you enter something wrong, you're going to get the wrong numbers at the end. So you have to have good data. Okay, and I think I've got mine all entered correctly. So commuters is going to be X, parking spaces is going to be Y. Commuters is in list 1 and parking spaces is in list 2. So we're going to go and we're going to make sure the scatter plot's turned on. And then we're going to hit zoom 9. And there's the scatter plot. So a little sketch of the scatter plot, so I know what you were looking at. It looks something like that. Again, it doesn't have to be perfect. Just close enough that I can get a general idea of what it looked like. Okay? Does there seem to be a linear relationship between those two variables? Yeah, it does look like one, because it looks like it is kind of traveling uphill in a tight band. So yeah, there's probably a linear correlation. So the scatter plot appears to show a linear relationship. So then it tells us find the correlation coefficient. Is it strong or weak? Find the coefficient of determination. and find the line of best fit. So from there, we go Stat, over to the Test menu, down to the Linear Regression T-Test, and the X data is in list 1, the Y's are in list 2, the frequency is still 1. HO says there is no relationship, so H1 says there is a relationship, that rho is not equal to 0. The equation goes in Y1, and all we have to do then is calculate. And the correlation coefficient is toward the bottom of that screen. So the correlation coefficient is R, and R rounded to 3 decimal places is 0.901. And since 0.901 is close to 1, there is a strong correlation. There is a strong linear relationship between commuter numbers and parking spaces. So then it says, what is the coefficient of determination? That's R squared. And that's going to be 0.812. And that's 81.2%. And then to get the line of best fit, we're going to round this off to 2 decimals. So 4.88 would round to 89.49, and then delete the rest of that. And then 0.409 would change to 0.41 and delete the rest of that number. So our line of best fit for our data, the least squares line, is Y hat is equal to 89.49 plus 0.41 times X. And X is your commuters, and Y hat is the predicted number of parking spaces. Okay. So then they ask us if the number of commuters was 1,675, how many parking spaces would you predict? Well, that means what I'm going to do is I'm going to replace X with 1,675. And I see that I have 776.24 parking spaces. And that'd be about 776 spaces. And then it asks us how much of the variation in the line of best can be explained by the line of best fit. And the value of r squared gives us the answer to that. And that's 81.2%. So 81.2% of the variation in the number of parking spaces is explained by the line of best fit. And if I did the arithmetic right, that means 9.8%. That's 100 minus 81.2. So 9.8% is not explained by the line of best fit. It's due to something else. Maybe holiday shopping, maybe people going on vacation, other things. Okay? And again, we could do the hypothesis test. To see whether our conclusion is actually a strong or a significant conclusion. And we see that our p-value is 0.0022. It's not asked for, but we could still do it. And even if we take alpha to be 0.01, which is pretty small, we see that p is less than alpha. So we would reject HO, that the correlation coefficient is equal to 0, which means there's no relationship. And conclude that there is a significant relationship between the number of commuters at that station and the number of parking spaces at the other stations. Okay? Yes?
100 minus 81.2 is 18.8.
Oh, thank you. I should have actually done the arithmetic. Thank you for doing it. Okay? So is this making sense in terms of what we've been doing? Calculator's doing all the formulas. You have no formulas to do. Okay, quick review of the hypothesis testing part of it before we wrap up. If rho is equal to 0, remember that's the population correlation coefficient, there is no linear correlation in the population. That's always HO. That's what rho equals 0 means. This is always going to be H1, which means there is some linear correlation in the population. Or there is a linear correlation in the population. What you're trying to figure out, based on the p-value, is R strong enough to say that H1 is true. So what we do is we compute rho for the sample data. Actually, we compute P, not rho. By using the linear regression t-test. We do not do it by hand. And as we usually do, if P is less than alpha, we reject HO and state that there is a relationship between the two variables. And we say that R is significant, and that's because P was less than alpha, which makes R statistically significant. On the other hand, if we find that P is greater than alpha, then we will fail to reject HO and conclude there is no relationship between the two variables because the R value is not significant. It isn't close enough to 1 or -1. So we're going to do 2 examples and focus on the hypothesis testing part of it. The first question is, how much should a healthy Shetland pony weigh? A Shetland pony is a very small pony. It says, let X be the age of the pony, and it's interesting, you need to notice that's in months. And let Y be the average weight of the pony in kilograms. So this says that a pony that's 3 months old weighs 60 kilograms. And that a pony that's 6 months old weighs 95 kilograms. And by the time the pony is a year old, 12 months, it weighs 140 kilograms. In the next 6 months, it gains another 30 kilograms, and it's 170 kilograms. And then by the time it's 2 years old, this should be its adult weight. And that will be one of the reasons you don't predict the weight of a 5-year-old pony. Because if you tried to do that, what you see here is you've got an increase, a constant increase. Well, after that pony's 2 years old, you think he's just going to keep getting bigger and bigger and bigger till he dies? No, we don't either. We hit a point where we've reached our adult weight and leveled off. And the same thing with the pony. So extrapolation would occur if we tried to do this, and our answer would definitely be wrong. We'd probably predict that that 5-year-old pony weighed 400 pounds. And there's no way that that pony is going to weigh that much. So first thing we want to do is create a scatter diagram. So 3 months, 6 months, 12 months, 18 months, 24 months. 60, 95, 140, 170, 185. And then stat plot is on, so we're good to go on that. So Zoom 9 sets it up, and I should have deleted that equation because it happens to fit on what we're looking at. So there's your scatter plot. Does it look sort of linear? Yeah. Although if you look at the top of it up here, you can see where his weight was increasing faster in the beginning. By the time he's between 18 months and 2 years old, his weight gain has started to level off, which is why you don't want to do this. So the scattered diagram does make it appear that there is a linear relationship. So the older it gets, the heavier it is. So we're going to find the correlation coefficient. Stat, tests, linear regression t-test. Just go straight to the bottom and calculate. And I'm going to make a note out here so that I don't have to keep going back and forth. I'm going to write out here that the p-value is 0.0055. And it says that R is 0.972. Which is a strong correlation. So when it tells me if alpha is 0.05, is it significant? Well, the p-value is less than the alpha value. So we're going to reject HO, which says rho is equal to 0, and therefore there's no relationship, and conclude that yes, there is a significant relationship. And we can conclude that there is a linear correlation between the age and the weight of all Shetland ponies based upon that. Okay? And so far, everything we've seen has been a significant relationship. So you need to know maybe when it's not. And that's the purpose of our last example. Because our last example is the magnitude of the earthquake in the depth, related to the depth below the surface where it actually occurs. So the magnitude of the earthquake is X, and it's measured on the Richter scale. And the depth is Y, how many kilometers below the surface of the earth is the epicenter of the earthquake. So 5 kilometers below gave a magnitude of 2.9. Whereas if you doubled it to 10 kilometers, then the magnitude went to 4.2, or in another case went to 4.5. But then one that was 11.2 kilometers below was actually only 3.3. So it makes you wonder, is there really a relationship? So what we're going to do is we're going to look at the numbers. And we're going to look at the scatter plot. Does it look like there's a relationship? Does it to me. I don't see a real clear pattern. So I don't see a good strong linear pattern. Does there appear to be a linear correlation? No, there's no linear pattern that's obvious in the scatter plot. So we'll find the correlation coefficient. And notice here what the p-value is. P is 0.2411. That's a pretty big p-value. And R is 0.511. It's about halfway between 0 and 1. So it's not a strong correlation. There's some relationship there, but it's not a strong relationship. It's a weak relationship. And if we compare P to alpha, then P is greater than alpha. So we're going to fail to reject. And that means there is no evidence of a relationship. So don't just jump in and complete a problem without actually looking at your scatter plot first. And if you don't see a linear pattern, chances are there's not one. Okay?